you give a 60 to 120 second commercial on what your poster and or demo is about.
Okay, so this demo shows to boot RISC-V UEFI firmware to UEFI shell with some device just like VGA, keyboard, USB support, and timer interrupt.
My name is Sam Falvo. I'm actually I'm actually the founder of the Kestrel project. And as you can see here, I actually have the Kestrel running. It's 64-bit RISC-V emulation environment. And just to prove that it is actually not just a static bitmap, it's actually doing something. So if you'd like to see this up close, and you'd like to learn more about what a home computer, not deep embedded, not supercomputer, but a home computer built around RISC-V might be like, feel free to contact me. I have a poster session out there, and looking forward to talking with everyone who's curious about it. Thank you.
My name is Celia. I'm a graduate student here at UC Berkeley. I have two posters, and if you'll allow me, I'm going to go out of order and talk about Boom first. The Boom is the processor I'm working on. What? No pun intended. Yeah. Hey, you're the one that put the order here. So the first thing is a processor I've been working on called Boom, which is the Berkeley out-of-order machine. That's a superscalar out-of-order processor that implements the full RISC-V 64-bit ISA, RV64G ISA. It's synthesizable, so although I'm targeting ASIC, you can put it on an FPGA, and it implements the privileged ISA, so I can boot Linux and run spec workloads on it. It uses the Rocket chip infrastructure, so you can just kind of replace the Rocket core with the Boom core, so that works pretty well. And the big news is it's now open source, and I'll be giving a talk on it tomorrow. So you guys can now download it, play with it, improve it, tape it out, whatever you want. Now the question is, how do you verify something like Boom? And so that brings me to the first poster, which is on RISC-V Torture, which is an internal tool that we use at Berkeley. There's a lot of contributors to Torture. I'm just kind of the spokesperson. And the way that Torture works is you have a library of small code snippets. We pick from these randomly, randomize the inputs, and then stitch them together, so you end up with a very interesting adversarial program. And then you can run it on your chip under design, and you can run it on Spike. And at the end of the program, you dump the register state, and you compare them. And it doesn't just have to be Spike. It could be another processor or an older version of the processor. And it's a pretty useful tool. It will humble you. It will find bugs. If anyone is building a RISC-V processor, I really recommend that they use this as part of their arsenal. And I'm interested, the news is that we've now open sourced this. So I'm interested to see how other people use it and see if maybe there's other contributions or improvements that we can make to this. So thanks.
Hi, I'm Joel from VectorBlocks. We built a tiny RISC-V IM to run on FPGAs. We built it to compete with things like Neos or Microblaze. So if you want to run RISC-V code on real hardware, or soft hardware, I guess, then come take a look at what we got.
Hi, I'm Tony. I'm an undergrad at UC Berkeley, and my poster is about the genealogy of the RISC-V instruction set. So you can find the precedents for the 32-bit RV32G instruction set. There's 19 ISAs in the poster, and there are 122 instructions. 117 of them have precedents, and 5 of them didn't have precedents among the ISAs that we looked at. And 98 of the instructions in RV32G appear in at least 3 different ISAs from the various ISAs that we looked at. These ISAs include the various UC Berkeley RISCs and Deluxe, and there are also the proprietary ISAs, so the DEC Alpha, the Spark, the ARM, and a bunch of other ISAs. So I think it's pretty cool, so you should come check it out.
Hi, I'm Andy. I'm a researcher from ETH Zurich. I would like to present to you Palpino, which is a small RISC-V based SoC that we were developing in the last couple of months. It is available for RTL simulation, FPGA, and for ASIC. We are currently working on taping out our first chip for the end of the month. This is done as a student project by Florian Zaruba, which is also here. Say hi. We are also working on open sourcing the whole platform, which will be done as soon as possible. We are currently actually only waiting for the final approval from the head of our university, so if everything works out, it will be up on GitHub by the end of the month at latest. So if you're interested, I'm also giving a talk about it tomorrow afternoon. So yeah, come check it out.
Hi, I'm Yawn again. So I'll be demonstrating 2 instances of the Groovy Phalanx system, which, as I said, is a work in progress. One is on a Xilinx Kintex KCU105, which is about a $2,500 card. That's the 400-core system. And I'm also demonstrating the same thing on a Digilent Arty, which is a little Artix 735T, which will have about 32 cores. And you'll get to see what the development environment is like as I'm trying to bring up message passing on the Arty. So, thank you.
Hello, I'm Sergey Khabarov, and I would like to present our current implementation of the navigation receiver supporting signals of the GPS, GLONASS, and Galileo systems. And I hope to present of our result of our development tomorrow. So that's all.